If you click on your
Good
image,
morning, good evening, good afternoon, everybody, wherever might be. It is my great pleasure to introduce my mathematical nephew, friend, and collaborator, Gilles de Castro. He will tell you about our joint work on extended path homomorphisms of directed graphs. It's all yours, Gilles. Take it away.
Okay, so thank you for the introduction. I think people, well, okay, so this is a joint work of Piotr, Francesco, in one part of the talk, and in the other part is Piotr, Mateus, and Elizabeth. So just to start, so this is part of this project on operator algebras and algebras that one can see. And the idea is that we want to use some combinatorial objects to study sister algebra and algebras in general. And then they have several applications, for instance, in symbolic dynamics, then non-commutative topology, classification of sister algebras. So we can really use these combinatorics of the graphs to study these kind of algebras. And then we are tackling one of these problems. I'm going to state the goal a little bit later in the talk. But basically, the idea is that we want to study this kind of algebras by looking at the graphs themselves. So that's why we can see these algebras in some sense. So this first slide is just to put some terminology. By a graph, I mean a directed graph. So we have these two sets of vertices and edges, and have these two maps, the source and target maps. There's some hypothesis that we usually don't say, but we usually think that these two sets are disjoint. So vertices are thought to be paths of length 0 and edges paths of length 1. And then we have this very important class of vertices, which are the regular vertices, in which it can only emit a finite amount of edges and admit at least one edge. So there are edges leaving and finite many of them leaving this vertex V. And then this is notation for the regular vertices of E. Well, another thing that's very common for graphs is that we have this notion of paths. I already talked about these paths of length 0 and paths of length 1, which are the vertices and edges. But in general, for positive integer, a path is just a sequence of edges. And the convention that we are using is that the target of one edge is the source of the following edge. So target of ei is the source of ei plus 1. So there is the other convention, but I'm going to use this one. And for paths, we can also define the source and the target of this. So the source is just the source of the first edge, and the target is the target of the last edge. And sometimes it's going to be important to make a difference between the map when applying to all paths, and then the map when applying just to edges. So that's why this PE is the paths of E. And if it's just E itself, it's just applying on edges. Yeah, this is important when we take the pre-images of vertices. And in particular for vertices, we also define the source and target to be the vertex itself. And as a matter of notation, this FPE is going to be the set of all finite paths in E. And we can also define infinite paths. It's not going to be playing a very important role in this talk, but we can also define infinite sequences with the same condition that the target of edge is the source of the next one. Or this should be for all I greater or equal than 1. And then now there's only one at the source, there is no target because there's no ending for these paths, and then IP is just the set of infinite paths. Another thing that's going to be important is that we can concatenate paths. So if we have two paths, certainly the target, a finite path, so the target of one path is the source of the other, we can concatenate, and this concatenation is going to be a new path. And we could do the same thing if x prime is also an infinite path, but as again, we're not going to need this here. But whenever we have this concatenation, this path x, you're going to say it's an initial subpath. Sometimes I just say beginning. So x is the beginning of this path, x prime, or it's an initial subpath. And X itself can be a vertex, and if it's a vertex, this concatenation is just forget about the vertex. So X prime is just X prime, and when X is a vertex, so all of X prime is a vertex, then concatenation again is just X itself. And we can define a partial order on paths just by saying that a path is smaller than the other, or again, it's an initial subpath of the other. Then we use this notation. And in particular, sometimes we need this kind of a strict order relation. So then we remove the equal sign. So it's when you have this strict relation, it means initial subpath, but they are not the same. So the length of X is smaller than the length of X prime. And finally, if it's either one of the other, we say they are comparable. And we use this notation for the relation between X and X prime. So this is going to be important later in the talk. So this is kind of just a basic terminology on paths. If you've seen some talk on graphs, you've probably seen this several times already, but we just need to make sure about the terminology. So something that is one of the tools that we can use to study this kind of algebras of graphs, both the sister algebra and left path algebra and compact algebras, all these kind of algebras, is using inverse semigroups. So an inverse semigroup is just a semigroup. So it just has one operation, which is associative. And we ask that for every element, there's this notion of a kind of inverse, or sometimes called pseudo-inverse. So the idea is that it satisfies kind of the relation of our partial isometries in sister algebras. So S star S equals S, and S star equals S star. There's another way of defining it is instead of asking this to be unique, you ask just the existence, and then the uniqueness is equivalent to the set of idempotencies being commutative. So it's another way of defining it. Actually, for proving that it's inverse semigroup, sometimes easier to instead of finding a unique inverse, to just prove that the idempotencies are commutative. And there's a partial order defined on this inverse semigroup. There are several ways of writing this partial order. One way of writing is that S and T for elements in this inverse semigroup S is less or equal to T if S star T equals S. So how to interpret this is there's as we know for graphs, for groups, as the GILLES theorem that says that every group can be seen as a group of bijections. For inverse semigroups, there's a similar theorem, which is the Wagner-Preston theorem, which says that every inverse semigroup can be seen as a semigroup of partial bijections inside a set. So partial bijection is just a bijection between subsets of certain given sets. And just so the relation, we're just saying that S is less or equal to T if the domain of S is less or equal to, it's contained in the domain of T, and when they apply S to this subset is equal to T applied to the subset. So, and then this S star is kind of I think here we are restricting the codomain, but we could do similar saying that S is equal to T S star S. So we would be restricting them. So as I said, there are several ways of writing this partial order, and I just chose one of them here to write it here. So since we're interested in graph algebras, we need to know what kind of inverse semigroup we studied for graphs. And then the idea is that we can write this set of pairs of paths, so finite paths, in such a way that the target of alpha equals the target of beta. And you add this element 0, which is in the sense of a partial bijection, just the empty set or the empty function. And the idea here is that when I've seen this is that this alpha beta, if you know graph sister algebra, just S alpha star, S alpha S beta star, so no star alpha, S alpha S beta star. Or in the first paper where they consider this kind of inverse semigroups, if you're thinking about partial bijections, you look at the set of all finite paths. So basically beta star is removing beta and alpha is gluing alpha back. So that's why they need to have the same targets. and this is going to be partial bijections on finite paths. So this is another way of looking at this. And we need to know how to multiply these things. And the idea is that this multiplication is we remove gamma, remove delta, glue gamma at the beginning, then remove beta, then glue alpha at the beginning. But in order to do that, we need to be this beta and gamma to be comparable. If they're not comparable, we just say it's 0. But if they are comparable, then we see which one is the beginning of the other. So if beta is the beginning of gamma, we just remove beta, and the remainder we glue with alpha. And if beta is big, so if gamma is the beginning of beta, then we remove gamma and then put beta primes in delta. And when we look at the order, so we can see paths inside the inversing group by considering pairs where alpha equals beta, so alpha alpha. And the comparison for the inversing group is actually the opposite of the comparison of the initial subpath. So elements which has a smaller path actually are bigger in this sense, because again, if you know a little bit more about these graphs, especially the groupoid model for graphs, the idea is that this alpha beta is going to be in the groupoids. It's going to be triples where the first element starts with alpha, the second element or the third element starts with beta. And then the bigger the alpha and the beta, the smaller is the set. So the smaller is this kind of cylinder sets. So that's why it's kind of opposite of the definition that I gave before. So this is the inversing group. There is also, it can be written as a universal property. I'm going to talk a little bit more when I show the slide with the relations. And if we are taking these inversing group routes, one way for defining graph algebras or path algebras, well, the usual path algebra we do not define, but we can go directly to these compath algebras. And the idea is that we just take the same group ring. So as a vector space, just the free vector space generated by the set, the inversing group. And then the multiplication is just the multiplication of the inversing group. But the thing is that because the inversing group has a 0, we want the 0 of the inversing group to be the 0 of the algebra. And that's why we take this quotient of the inversing group, the idea generated by the element 0 of the inversing group inside this free module or this free vector space. And when you do this, sometimes it's called the contract same group algebra. And then this is just exactly the compath algebra. I'm going to give the relations later, but this is one of looking at the compath algebra. And then, as I was saying before, this alpha beta, when you see inside the algebra, we just write this as this kind of self-host beta star, or if you're not using S, you just say this is alpha beta star. This is generators of this algebra. And in particular, if you just have a finite path, you just want to say about S alpha, then alpha is correspond to this alpha and the target of alpha in the second coordinate. And then the life path algebra is just the quotient of the compath algebra by this ideal, the ideal generated by the set. So the set is just taking all regular vertices, and you want the regular vertices to be the sum of S, S, C star, where E, the sum is over all E's that starts from V. Because V is regular, there's at least one edge, and it's finitely many, so the sum is not 0 and it's well defined. Okay, so this is one way of defining these algebras if you go from the inversing group route. Another way, if you want to define directly using generators and relations, if you want to talk about the left path algebra, you take 3 sets, one set associated with vertices, one set associated with edges, and then another copy of sets of elements associated with an edge. Sometimes this is called ghost edges. So Tomek has a question.
Tomek, just go ahead.
Yes, I have a question. So I waited for some time, but probably was not so important that you passed above this. I have a question. Could you come back to the definition of your equivalence relation on paths?
This one?
No. Yes. No. Before. Yes, it is here. Finally, we write that x is equivalent to x prime. Do you really mean the equivalence relation here?
No, it's not an equivalence relation, just a relation.
Okay. Thank you.
I think the last time that I talked about this, I think Adam made the same point that we are using the symbol for equivalence relation, even though it's not really an equivalence relation.
It just means comparable, right?
Yeah, it just means comparable. Yeah.
Okay. Thank you.
Okay, so going back here to the definition of left-path algebra, so another way of looking at this is, so you take these three sets and then you have all these relations. So basically it's saying that vertices are idempotents, which are orthogonal, so the product of the zeros, they're different. And here if you, basically E1 and E2 just saying that we are respecting concatenation of vertices and edges. So the source of E, when you concatenate with E, just a source of, it's just E itself, the same thing for target. And when we take these stars, which is the ghost edges, they have the target and source exchange. So you use here the target of E is the source of the E star, and similarly, the target of E star is the source of E. So they have the second relation. So for sister algebras, you don't need this because everything is already had a star. And then this CK1 is just saying, if you look at in terms of partial isometries, it's just saying that the final projections are orthogonal, and if they're the same, so F is equal to C, then it's just the source of the lithography. This is where people don't like this convention because it should be the initial projection, the initial projection is associated with the target, so that's why some people use a source here, and then every convention is a little bit different. And finally, this CK2 relation, which is the relation that comes from the Kuntz algebra and the Left algebras, which is just saying that a vertex which is regular is written as the sum of SESA star. I didn't write the compath algebra, that if you just remove CK2, then you have the compath algebra, and then with CK2 you have the left path algebra. And I'm not going to talk too much about sister algebra, but the graph sister algebra is the same thing, just the sister algebra and universal sister algebra generated by the same relations. Or because we have a star algebra here, we can use, when you take K to be the complex numbers, you just take the universal algebra, sister algebra of this star algebra. It does exist because since V's are going to be idempotent, actually they're going to be projections, so they have they're not bounded by one for every representation. The SCA partial isometries, again, they have they're not bounded by one for every representation, so the sister algebra, inverse sister algebra exists in this construction. Okay. Now, to state the goal of this project is that basically we want to make the construction of graph algebras, left graph algebras, compath algebras, graph sister algebra, all these algebras, and then the top is sister algebras. We want to make this construction functorial, and then the question is what kind of morphisms we define between graphs. And then the point is that we want these morphs to be simple enough that we can really use the combinatorics of the graphs, but we want them to be broad enough that they include a lot of examples that we are interested in studying. So a couple of weeks ago, Ralph gave a talk on groupoid actors. So we can define a morphism between graphs using groupoids, but I'm not going to talk about this construction in this talk. We're going to go in these more simpler definitions of morphisms that we are using. And then the groupoid, every morphism like here can be seen as a morphism between groupoids, but I'm not going to talk about groupoids in this talk. Okay, so the first definition, this is what one would think about when you think about graphs, since you have these four elements to define a graph, the set of vertices, edges, and the source and target map. Basically, what we do is just take two functions, one function between vertices, one function between edges, and we want this function to preserve source and target. So you have this commutation here, or this composition. We can write this in terms of a diagram, but basically we want the source and target to be preserved. And well, the identity is a map like this, composition of maps like this again is a map like this. So we have a category, and in this category of graphs. So in all categories that I'm going to talk about, all objects, except when I talk about algebras, but then in all graph categories, all objects are all directed graphs. And just the morphs are going to change. So this one is OGs, is O for the original graph homomorphisms. And then we want a construction of a homomorphs between the algebras using homomorphismal graphs. And the formula that we use now, this is going to be a contravariant functor. And then the formulas that we use to define this homomorphs between the algebra is just taking a vertex, and we sum of all, it should be S, not P, but just sum over all vertices which are in the preimage of V, and here we sum of all edges that we in the preimage of F. So in order for this to make sense, so that's why you have this P here. This P is to mean proper. We want these preimages to be finite, because otherwise the sum is going to be an infinite sum. So we want this to be finite. And if it's empty, then this is 0. And then we need to show that this gives us homomorphs between the algebras. So if you only look at the proper, then we only have homomorphs between the path algebras. If you want to go to compath algebra, then you have this TB, which is target bijective. So this target bijective, which is, I'm not going to write here, but this is what is needed to show that this satisfies the CK1 relation. Because when you have this phi star, so you have this SF star and SF prime, then you have the sum, and you kind of have a sum for C prime, and then when you multiply, you need to make sure that what remains is exactly the map phi star for the vertex, which is the target of F. So that's why we need this TB. I'm going to write this for relations a little bit later, but and finally, because you need to also satisfy CK2, you need this regular, if I recall correctly, C is for contravariant. So C is contravariant regular, and it is easy, just say that the preimage of regular versus on F is regular versus on E.
May I make a quick comment?
Yeah.
It's mostly for the local folks here in Floripa. So next week at the function of this seminar, I will unravel it a little bit more, because kind of inspired by Tomek Maszczyk, Mateusz Lobiel and I, we classified all such homomorphisms. And this is very nice and extremely simple. And I will focus on moves related to that stuff. But I thought it was a good point to make a local announcement that if you want to know more about this stuff, it's my talk next week.
Okay, I'm going to talk a little bit about moves at the end of the talk here, at least the outsplit, but I won't talk too much about moves. Okay, so the second kind of homomorphs that we study is this path homomorphisms. And so the idea is that there are, as I said, there are some examples that when we look at the algebras, you know what homomorphs you want between the algebras, but you want them to be homomorphs between the graphs. And then these original ones that we just send verses to verse and edges to edges, sometimes it's too restrictive and it does not give the examples that we want. And so another idea is that we, instead of define a map between just vertices and edges, we define between all finite paths. We still want to send vertices to vertices. This is something that we're going to generalize when I talk about the extended path homomorphism, but for now, we are sending vertices to vertices. And now edges does not need to be sent to edges. Edges can be sent to any finite path, including you can send an edge to a vertex set or an edge to some other paths with length greater than 1. But you still want to do this map to preserve sources and targets. And then the other thing is that we want this to be multiplicative when it makes sense. So if x and x prime can be concatenated, then their image can also be concatenated by the second item, and you want this to be multiplicative. And another way of looking at this, for those who know, is that finite paths on E can be seen as a category itself, where the objects are vertices and the morphisms are paths. And basically, this is just saying that this theta is a functor between these two categories. But I'm not going to need to look at this in the setting, so we just look at functions which is multiplicative, send vertices to vertices, and preserves source and target. And then this category of graphs in this path homomorphism is going to be denoted by PG, so P for paths. And again, we want this construction to be functorial. I'm going to talk how the formula goes, but basically, we're just going to send a vertex to its image and an edge to its image. So there's no sum here, but we need to then to satisfy also the property, the relation that left path algebras satisfy. And so we need to impose a little bit more on path homomorphism in order to have a functor. So the first thing that we ask is theta to be injective on vertices, because we have that different vertex that are orthogonal, and then if you want to take the image, they also need to be orthogonal, otherwise you're going to have something which is not going to satisfy the relation V. So we need it to be injective on vertices. So it's enough to define a functor to path algebras. If we want to go to compath algebras, then again we need to make sure that CK1 is satisfied, and then we need this notion of monotonicity. It's just saying that whenever you have two edges such that their images, which are paths, are comparable, one is the beginning of the other, then the edges must be the same. I could replace this, let's recall to the comparability, it's definition the same. But basically, if the images of any prime are comparable, then they must be the same edge. So this is, again, this is to make sure that CK1 is satisfied. And then the last one, I won't go into too much details here because I want to give a different definition for regularity. But there's this one's a little bit harder to understand, but we need this, again, we need to make sure that CK2 is satisfied. So we need to take into account first these kind of edges which are mapped to a vertex, which are just a loop based on a vertex V. So then we have this condition on theta, but if it's another kind of a regular vertex, then we need this. Basically, we need that the images of edges are different between edges leaving V. So you have this restriction being injective, and then we have this condition as I said. I'm not going to go through the definition here because I'm going to talk about a little bit differently on how we can see the regularity. So this is the definition of the regularity that Piotr and Marius used in their paper. But now we saw that this definition is actually equivalent to another way of looking at it. And then the idea is trying to use the terminology that comes from inversing groups. So there's this paper by Huyaxo where he defines this tight groupoid and tight curves and things like that. And so we just adapted this to the case of graphs. Then we don't need to go to the inversing group. We can do directly on paths themselves. And so the idea of a cover is that we have this finite path A. So it's a finite cover, so we need this to be a finite set of paths. All of them has alpha as an initial subpath. And the second thing is that whenever we have another path which also begins with alpha, so alpha has alpha as an initial subpath, we need that this beta be comparable with some alpha I. So this is the notion of cover, as I said, that comes from the theory of inverse same groups that we have adapted for graphs. And in this cover is it's called orthogonal if the alpha i's are pairwise orthogonal in the sense that they are not comparable. So alpha y is not comparable with alpha j if you want to be this cover to be orthogonal. And then, as I said, then there is a different way of looking at regularity. So for a path homomorphism, this theta is going to be regular if and only if. So whenever you have a regular vertices on E, you want the image of the edges starting from V to be an orthogonal cover for the image of V. So image of V is a vertex. So you want these images of edges leaving V to be a cover for this state of V. And you need this injectivity. So we need this to have as many paths as you have edges leaving V. So this is another way of looking at it. So if we go back a little bit to the definition, basically this condition 1, 2, and 3 is ensuring that these p's that are in the image of edges leaving V, they form a cover for the image of V. So this is another way of looking at regularity. And then the good thing about this cover is that whenever you have a finite path alpha and you have this finite cover, which is orthogonal, so it's an orthogonal cover for alpha, then you can write S alpha star as the sum of this S alpha as I star. So the idea is that if you take the target of alpha, you can put in the middle here S of these targets because of these E1 and E2 relations. But if the target of alpha is a regular vertex, then we can use the CK2 relation to replace this target of alpha with the sum of SE, SE star. So basically this S alpha, S alpha star can be written as a sum S alpha E, S alpha E star. But then the target of E, then for each E that we have in this preimage, you could have that as the target of E is also regular. So we can use the CK2 relation for some of these E's, but not for others, or you can use for all of them if they are regular, and then use the CK2 relation to increase the size of alpha, and then you can just keep doing this. And so when you use the CK2 relation several times, you're going to have a sum of this S alpha star, but then the lengths of alpha and alpha j's can be different. So the CK2 themselves is just edges, but as I said, when you apply this several times, you apply not all for all terms as the S star, but just for some, then we can arrive at different lengths. And the idea is that basically what we want in order to really use CK2 is you need this notion of a cover. And this lemma simplifies a little bit of the proof that of this theorem here. So the idea now, we go to the formula that we want to define for the homomorphs between the life path algebras. So if you have this path homomorphism, basically you just take this element S associated to X, and you map to the S associated with the theta of X. And then we have this category of path homomorphs, which are injective, convertices, monotonic, and regular. So we have this subcategory for all the whole category of path homomorphisms. And then you have this construction. So this is needed to show that TK2 is satisfied, this lemma. And then you have a functor between this the subcategory to the category of K algebras would give the left path algebras. So this I here is injector vertices, M for monotonic, and R for regular. Okay, so this is where I entered in the project. So one of the questions that we had is, okay, we have two functors. One is contravariant functor, another one is a covariant functor. And then there are some examples when studying this pullback of left path algebras where you kind of need both of them. So there are some results on pullbacks, which they call these the mixed pullback theorems, where because you need both of these functors. But the idea is that we want just one of them, just one functor. So we wanted this to be unified. And how we can do this, and then the idea is to use relations. So this is the paper by myself, Piotr, and then Francesco. So we unify these two functors. And then the idea is that, as I said, instead of looking at functions, we look at the relations. And we go directly as path homomorphism to relations between the set of paths. So we have a relation between the set of paths of E and the set of paths of F. Again, we are asking that vertices are preserved, so just preserved in the preimage. So we never have a vertex here in the second coordinate. The first coordinate must also be a vertex. And we want also that the relation preserves the source and target of paths. And then we can show that for relation, there's a very common notion of what is the composition. This is just for sets in general. So we just take this composition of relations. And when we do this for this kind of relations, we obtain a category. And now this category we call this RG, so R for relations. And we want to see the old categories as kind of subcategory of this one. So first for the contravariant functor, we decided this to be contravariant, so the relation from E to F is going to be, for the above homomorphism, the original one, the relation is also going to be from E to F. So this is just a graph of this map. When we extend I guess I forgot to say, but here we have the two maps, one defined on vertices and another one defined on edges. But we can easily extend this to be a function between finite paths. We just, if you have a sequence of edges, you just apply phi 1 to each of these edges. And because it preserves certain sources and targets, we again are going to obtain a path on the other on F. So that's why we can use phi here as a function between finite paths. And so this is just a graph of this function. And for the path homomorphism now, we define this should be from E to F, not from F to E. The relation is from E to F. The homomorphism is from F to E. And so the relation is just the transpose of the graph. So we just take the graph and just instead of looking the image in the second coordinate, we look at the images in the first coordinate. Okay, so this is how we see the original categories as subcategory of the relation category. And then we actually show that this is indeed, there's kind of this invariant of categories in this set. So because for path homomorphism, we are changing, it's going to be a contravariant functor. We actually have the opposite of the PG category as a subcategory of our relations. And And as I said, that the map the phi is just equal to r phi, and then map of theta goes to r theta. So this is within in the right direction. Okay. And now this is something that it took a while for us to find out the properties that we needed to get a functor from this graph, well, a subcategory of this graph relation morphism. So we need more structure. And then we have this notion of unadmissible relations. I'm gonna give all the property that we need this relation to satisfy. Because we want to have algebra homomorphisms, we need these two properties. One is the multiplicative. So if we can compose x and x prime and y and prime, then the composition should be, or the concatenation should be also be related. But we also need to be able to decompose in the first coordinate. So if the second coordinate is a concatenation, then we need to be able to decompose this x bar as a concatenation, where the first one is related to y and the second one is related to y prime. So this is to make sure that the formulas for the algebra homomorphism is going to be multiplicative. But we also need this properness because we again going to use as a sum. So we need to ensure that the sum is finite. So we need this properness condition. And then now the remainder is kind of be a mix between the two old categories. So we have this. I think this is kind of. I think we changed the terminology. I think this is the old terminology that we are using. I think now we are just saying that it's vertically disjoint. But anyways, we just need to make sure that whenever I take vertices on E0, this is gonna be a map or a partial map. This when I'm looking at the other way that we are writing as in the paper is that the preimage of two vertices on F0 must be disjoint. So this is again just to ensure that it's similar to the path homomorphism between injective vertices.
Let me quickly comment that this assumption that it's restricted to vertices is very important, because we have a very simple example. Imagine a graph which has just one loop and a graph which has just one vertex. And then you have infinitely many paths, I mean, all winding numbers of composing a loop with itself, and all of them will shrink to one vertex, okay? So by all means, I mean, you can map infinitely many different paths to just one vertex. But it's only one, if it's a vertex, one vertex can be mapped to one vertex. You cannot identify two different.
Yeah.
You cannot have two different vertices here combined into one.
And then later we realized that there's an easier way to write it. This I think I was taking from an old slide. And then we have this target by directivity, which was for the original path homomorphisms. So now I can explain a little bit more. Is that we take all paths that are related to F and all vertices which are related to the target of F. So because the preimage of vertex is vertex, which is in the definition in the previous slide. So here we only have vertices, and here we have finite paths. And then we add to this target function between the paths related to F to vertices related to the target of F to be bijective. So this is to ensure part of the CK1 relation, but we also need monotonicity. Now it's a little bit different, is that whenever you have these two pairs, so this is R1 just to make sure that F and F prime are edges. So we have these two pairs which are in the relation. If the X and X prime are related or are comparable on one of the beginning of the other, then not only the edges must be the same, but the path themselves also must be the same. So the pairs are the same. So this is to ensure this to ensure the CK1. So up until here, you have a functor to the category of K algebras, but you given the compact algebra. And finally, if you want regularity, this is kind of the notion of cover again. Is in the sense that so whenever you have a regular vertex V, and you have anything which is in the preimage of V, and then you have a path step of this in this element U, which is in the preimage of V, then this X must be comparable to some X prime which is related to a vertex F, which starts in V. So in a way, the paths that are related to edges leaving from V must be covers, but now we do not have only one vertex, we have several vertices here in the preimage, but for each vertex we need this cover for you. Okay, so this is kind of a lot, but we shown that this composition of homomorphisms which are admissible is again admissible. The proof is a little bit tricky because we need actually, especially regularity, which is the hardest part, but even the other ones, the multiplicative, the composables also is a little bit tricky. And we have a category, and the old categories are subcategories of this new one. So we have a subcategory of all the graphs for all relation morphisms to these admissible relation morphisms. And when you have the inclusion of the original graphs in the relation morphism, when you take the intersection of the admissible, we get exactly the old one. And the same thing for path homomorphism. Of course, now here we're taking the opposite because we have a contravariant functor. And then this is the result that is in this paper with myself, Francesco and Piotr, in that so there is a contravariant functor. So as again, because of relation, it's itself dual. We could choose to be covariant or contravariant, but we chose to be contravariant to use the original homomorphisms in the same direction. So there's this contravariant functor from this category for admissible relation morphisms and graphs to the category of K algebras, scenographic left path algebras, and the admissible relation morphisms. And then the formula that we have for the homomorphisms is kind of the same as we have for the original path homomorphisms, in the sense that we are summing over everything in the pre-image. So, but now it's instead of being a pre-image of a function, it's a pre-image of a relation, but the definition is basically the same. And because we are asking the relation to be proper, this sum is finite. And then, as I said, all the other properties that we ask for the relations is to ensure that we have maps which are satisfy all these 5 relations defining the left path algebras, V, E1, E2, CK1, CK2. There's this one going back a little bit here. If you want to have functor to F algebras, then this is something that kind of surprises that this target activity we need, which was not needed before. We need targeting the activity to be part of the definition in order to obtain a functor to F algebras. And we had an example in my previous talk. I gave the example here, just recalling, but we need a little bit more to have this path homomorphism. Then we shown that there's actually no subcategory for RG that contains the category if you just go to here, POG and PG up. So there's no subcategory for RG containing these two and making the construction of F algebra functorial. Anyways, but the formulas are all the same in path algebra, compact algebra, left path algebra, and this, as I said, this is something that I've talked in a previous talk, I think it was, I don't know, last year or 2 years ago. And okay, so this is, we have several examples where we can use this construction. But now I want to talk about one example in particular that now motivates us to go beyond these relational morphisms. And the idea is that if you take these two graphs, both of them gives us 3x3 matrices over the field K. And there is a very natural relation that we can define between these two graphs. So we can map U1, we are relating U1 and U2 to V1, and then U3 to V2. And then we have this E2 being related to F2, and then the path E1, E2 related to F1. So this example is not a path homomorphism nor a path the original homomorphism graph. So this is really a relation. It's kind of a composition of the other two. So this is really a relation, and this induces a homomorphism using the formula before. And because we are talking about 2x2 matrices, which is simple algebra, this homomorphism is an isomorphism because it's finite dimensional, and so we know that this is an injective, so it's an isomorphism. And when we look at the inverse, what happens is that the inverse of this E1, we need to use stars. So the inverse for this homomorphism, we need to use stars. And so because we use stars here, and if you go back to the formula of the homomorphism coming from relational morphisms, there's no stars over here. So this inverse cannot be found using a relational morphism. We need something else. So the first idea was trying to use extended graphs, which in a way we do, but the problem is that in extended graphs, we do not have the CK1 relation. So it's a little bit harder to work with the algebra of extended paths. And that's why the idea is to use the inverse semi group, because now for the inverse semi group, we do have the CK1 relation, and then things simplify. And so that's why we came up with this definition of extended path homomorphisms. So it's basically just a homomorphism between the inverse semi groups, and we want is to preserve zero. I'm not sure. I don't think I've written this in the slides, but basically, if you have a homomorphism between inverse of same groups in general, forget about zero. If you have a homomorphism between same groups, then this is naturally gives a homomorphism between the algebras of these same groups. But because we are taking the quotient with this zero element, the ideal generated by the copy of the zero element in the algebra, we need this to preserve zero in order to get a homomorphism between the compact algebras. And then, again, we have this notion of regularity, which is, it's usually, except for the homomorphism between graphs, which is easy, just the image of regular vertex, all the other definitions are usually tricky to say. But what we need here, okay, so first of all, when you look at this inverse same group, we have the vertex themselves are seen as this pair. So we have a regular vertex on E, and we want to see this regular vertex on the inverse same group. You have the pair UU. Recalling that the inverse same group are pairs of paths which have the same targets. And then again, this is kind of looking at the inverse same group theory in the notion of covers for inverse same groups, that whenever we have an element which is smaller than this phi UU in the partial order of inverse same groups, then this T must be comparable in a way. So in comparability in terms of inverse same groups, we want this product to be different from zero. So we want this to be and having multiplication different from 0. But the image of phi EE, where this E is some element starting with U, so some edge. And so this is some edge starting with U. And then you want this product to be different from 0. Again, this is very motivated by the definition of cover for inverse groups. But if we want to use covers for graphs, we can rewrite this definition in a different way. So let's go through this proposition now using covers. So this extended path homomorphism regular, if you only if, so we have the, again, you need to look at the regular vertex on E. And now let's look at, first of all, this U. As I said, inside the inverse semigroup, we're seeing this as this phi UU. And because this UU is an idempotent, the image is also an idempotent. And we can show that idempotents on this inverse group are just pairs which are the same, first coordinates equal to the second coordinate. So this phi UU is mapped into this beta beta. So this is something that is different from before. So before, in all other three definitions, we need the vertex to be mapped to the vertices. So now a vertex can be mapped to a path. But now this path is to be interpreted actually to be beta beta star. So not the path itself, but the element beta beta star. So if you have this beta, so being the image of U, so beta is the image of IUU. So we can see first of all that because E is beginning at U, so the source of E is U, then the image of IEE must be of the form again, it's the same path in the first, second coordinate, but this path must be a continuation of beta. So it must be beta as an initial subpath. And now if you look at this continuation for each E, you have this continuation of beta, which you call that delta E. So this continuation must be a cover for the targets of beta. So that's how we compare these two other definitions. I guess there is another way of looking at it is that the beta delta E, if you still consider the beta, so the set of beta delta E is a cover for beta, or if you just remove beta and then have the delta E as being a cover for the target of beta. And the good thing about this is that when you look at the lemma that I've written before, that whenever you have a cover, you kind of have this CK2 relation in a way. This equivalent definition or this equivalent way of looking at the regularity gives us a nice way at looking at the formulas for the algebras later, especially for the CK2 relation. Okay, so now we want to talk about functoriality. So this is, I guess, something that I was saying before. So if you have this extended path homomorphism, because this is homomorph between semigroups, we can always define a homomorph between the algebras of these inverse semigroups or the inverse semigroup. It doesn't even need to be an inverse semigroup, just semigroup algebras. The inverse is going to be, if you look these algebras as star algebras, then this is going to be a star homomorphism. But because the compact algebra is the quotient of these semigroup algebras by the ideal generated by the cop of 0 here, as I said, we ask this phi to preserve 0. And because it does, we can just look at the quotients, and then we have this homomorph between the compact algebras of E and F. I just want to point out that before, when we are talking about the relations, the functor was contravariant, but the original functor from path homomorphisms is covariant. So again, we have a covariant, going to have a covariant functor, so it's from E to F here, and from the algebras again, it's from E to F. So as far as the compact algebra goes, is very direct, just because the compact algebra, as I said, is just this quotient to the semigroup algebras. But we want to go a little bit further. We want to go to the left path algebra. Then we need to take into account the regularity. And then that's where this equivalence that I had before between regularity and this notion of cover, that's where it takes place. And then that's also how we prove that we really have a category, because we need to show that the composition of regular is regular. Using the definitions usually is very tricky. Even for relation morphism, again, when you show that the composition of a regular relation morphism is again regular, what we actually do is showing that this regularity is equivalent to have an expression in the left path algebra and then basically preserving the ideal in the compact algebra. So the idea is, so it is regularity. So if you look at the phi UU, as I said, if I go back to the previous slide, so phi UU is going to be beta beta star. So this S of phi UU is going to be S beta star. And because we have a cover, using that lemma that I said before, when we have our cover, we have this kind of a CK2 relation. So this phi EE is S beta delta E star, and then the sum is equal to beta beta star. And then the good thing is that so we have this equivalence between regularity and this equality being true. And then the third one, between the third one and the second one is just well, okay, this is the proof themselves is not that easy, but to show that the composition for regular is regular is really easy to see in this third equivalence statement here. So this statement that the ideal is into ideal is really easy to see that it preserves composition, because if you, let's say, apply to some psi star C here, we're going to have a psi star of phi f. It's going to be containing the ideal of the third graph. So this third one is very easy to show that it's preserving the composition. Regularity is not easy at all, but once you have this equivalence, then we can see that the composition is regular. Okay, so because we are saying that we have some extended path homomorphisms, we need to compare the old notion of a path homomorphism with this new one. And the formula is rather straightforward. We take this path homomorphism because for this extended one, we started directly from the compact algebras. We asked the path homomorphism to be already injected on vertices and monotonic. And if you have this path homomorphism like this, then the formulas themselves just in 0 to 0, because we want this to be an extended path homomorphism, which is still part of the definition. And then the second one, so theta itself, since it's a path homomorphism, actually is a function between finite paths of E and finite paths of F. So we can apply this theta in alpha and theta beta. And because theta preserves targets, because target alpha is equal to target of beta, then the target of theta of alpha is going to be equal to the target of theta beta. And so we define this like this. And then this is going to be a extended path homomorphism between E and F. And basically the idea for the first part is that if you look at the inverse same group, I gave the definition kind of in a concrete way. So it's pairs of paths satisfying the target being the same. But there's another way of looking at the inverse same group of a graph using, again, these universal constructions, in that it's the universal inverse same group generated by vertices and edges, satisfying all these relations V, E1, E2, and CK1. And because for path homomorphism, in order to have a functor to compath algebras, we need injective, inverse, and monotonic. The same basically the same proof that is done there to show that the homomorphism between algebra satisfies this V, E1, E2, and CK1 is the same for the same groups, because these four relations define the compath algebras. They are all multiplicative. There's no sums over there, and that's why we can show that this is again an extended path homomorphism. And if you want to talk about the regularity, so we had this notion of the theta being regular, which was that definition that, as I said, it's kind of difficult to parse, but it's equivalent to the notion using covers. And then, because again, for extended path homomorphism, again, we also have these equivalents using covers. We can see that the regularity of V in the sense of a path homomorphism is the same as regularity of phi theta in the sense of extended path homomorphism. So we really do obtain a functor between the categories. I'm going to write this in the next slide. So first of all, we do have a category for this regular extended path homomorphism. So we have, as I said, directed graph as objects for all of them. So now we have this category denoted by REG, so alpha regular, E for extended or extended path homomorphism, and G for graphs. And then the other one of path homomorphisms is, if you want the regular one, we need monotonic and injective inverting, and also need to be regular. And then this category can be seen as a subcategory for REG. Okay, so this is just the categories, but we also want the functors. And so this is still work in progress, but well, we have already proved this theorem, so that's why we can stay here. But the paper itself, it's going to be hopefully read by this year. And the idea is that if you have this extended path homomorphism, so a regular, whenever you have an element which is either an edge of or a vertex, so we want the image of this P using the inversing group homomorphism. And the idea is that if you have a vertex, it's just the vertex, so the target vertex is itself. But if it's an edge, we do not want to be edge, because the edge here is corresponding to PP star. And we want to really just be P itself. That's why we put the target here. So we have an edge P, so phi P, and the target, this corresponds to the edge inside the inversing group. This is going to be some pair alpha beta. And so basically what we're saying is that we're going to send P to alpha beta star.
I understand that WIP means work in progress, because
yes.
I read VIP and
yeah.
person
is VIP. And so this is defined as star homomorphism between the left path algebras. We need the regularity exactly to show that CK2 is satisfied. The other, all the other properties come before for compact algebras, just being homomorphism between inversing groups satisfying present 0. And then we have a contravariant functor, covariant functor from this category of graph with regular extended path homomorphism algebras. And this extends the covariant functor that you had before from path algebras, from algebras, or from just path homomorphism and to algebras. Okay, so before I go to example, I just want to say that, so for now, we kind of have the relation morphism, we have this extended path homomorphism, and then they are not really compatible in a way. So there is already an idea for extending relations to also the university groups. This is something that we're going to do in the future, that we want to unify both this extended version and the relation morphism version to just one of them. But for now, we are just taking one step forward, which is just looking at this extension of the covariant functor. And another thing that we also can see this using groupoids, as I said, I didn't write this in the slides, but because there's a very important relationship between the groupoid of the graph and the inverse of the graph, these formulas can also be seen using this notion of actors on groupoids in this Kunz-Krieger dynamical family that I think Ralph talked about 2 weeks ago. Okay, so finally, let's go to an example. So this is one of the things that is interesting about graphs is that we can, as I said, we can see the graphs and then we can try to look at the combinatorials of the graphs. And then there's a very important move. So this move is just a transformation of the graphs using some kind of formulas. And there's this very important move which is called the outsplit, which is something that already appears in symbolic dynamics. It's very important there as well. And the idea is that we take a vertex, which is not a sink, and we look at all edges and leaving W. And then we take a partition of this set into a finite joint union from non-empty sets. So this W is not a sink, but it could be an infinity meter. And if it is an infinity meter, when we take this joint union, we want at most one of them to be infinite. Or if it's infinity meter, exactly one of them is going to be infinite. All the others are going to be finite. Of course, if this set is finite, then it's already everything is finite. But in general, since we don't know if W is an infinite meter or not, we just say that when we take this partition, at most one of them is going to be an infinite. And then we're going to define this new graph. So first of all, this vertex W, where we are taking this disjoint union, basically we're gonna copy it as many times as there are elements in the partition. So we remove from the original graph, and then we, as I said, we take as many copies as we have sets in the partition. And we, of course, we want these to be new vertices. So this, just to represent it, this is a disjoint union. Okay, so for edges that leaves this W, we do nothing. But for edges arriving at this W, we need to copy it as many times as we have elements in the partition. So for each W, for this W, we remove all edges arriving at W, and we make as many copies of this edge as there are elements in partition. Okay, so we need to define what is the source and the target of these new edges. The original edges, the source and target are the same, but for the new edges, we need to know what happens. So the thing is that for the source, we just gonna take the source of E, and then we correspond to the first one if the source is not W. So basically, this is just this one here is just taking a copy of the original vertex and original edges. So basically, it's just the source of the original source of E if the source is not W. And when it's W, we look at where in the partition this E belongs. So if E belongs to epsilon J, then we choose this W to be in this partition. So, Tomek?
Yeah. Tomek? Tomek?
I have a question.
Yeah.
So in your partition, you are assuming that at most one epsilon is infinite.
Yeah.
Okay. So why at
Wait.
most one?
We don't really assume it. I mean, it might be, but at most one, not more.
Yeah. So why not more than one?
This has to do with the CK2 relation.
I think it would still be an admissible homomorphism. I mean, you would really have a star homomorphism, but it would not be an isomorphism. The formula for the inverse would fail.
Mm-hmm. Okay, thank you.
Okay, so the source for the new for the original edges are the same. The source for the new edges, if for the new edges, if it does not start with W, it's basically the copy of the old vertices. But if it belongs to, it starts with W, then we look at where it belongs in the partition. Then we take the copy of W corresponding to that one of the partition, and the target is just the usual target if it's the original edge, and if you need to copy, you just take the index corresponding to its copy. So this is one way of writing this. So this is an out split at vertex W, and in the case that every epsilon I is a singleton, we call this the maximal out split at W. Because this is a finite union, if every epsilon I is a singleton, then W must be a regular vertex. It's a W, and then when it's the maximal split, we denote by this O hat. And so, first of all, we have the usual graph homomorphism. I guess I call here the admissible, which is the regular, target bijective, and proper. So these maps is just taking, basically just forget the index. So you want a map from EO for the outplate. So you want this map from EO to the original graph. So basically just forgets this index. So all this W, that's what's written that we are going to collapse to W again. All these copies we collapse back to W. And all the copies of E that we needed to make copies, we just collapse to the original edge E. So there's this map, and we can show that this map is an admissible graph homomorphism. So as I said, it's regular, targeted bijective, and proper. And so we have, because of the contravariant functor between the category where we look only at the graph homomorphisms, we have the map F star, which goes from the sister algebra or the left F algebra phi to the algebra phi O. And we want to look at the inverse of these homomorphisms. And the idea is that if you look at the outsplit which is not maximal, we can decompose the inverse using, first of all, this graph homomorphism, because when we're collapsing from E0 to E, actually we could collapse to kind of a smaller outsplit. I think we call a refinement if you go in the other direction. So we can always collapse the maximal outsplit to a partial outsplit. So there's always this map from this maximal outsplit to the original one. So we are collapsing corresponding to the partitions. And now we have, when we look at the formulas for the inverse, when you have a maximal split, then we can actually define this extended path homomorphism between this the graph of the maximal split and E. Because now the inverse, we do not need the sums for the inverse, we just need just one element. That's why we need to take the maximal split here. But when we compose, so this G, because it's a path homomorphism, which is have a contravariant functors, it goes from this algebra of it should be, yeah, it's the inverse. So it's go from the algebra of EO to the algebra of EO hat. And phi star is a covariant functor, which goes from the system out of EO hat to E. And then when you take this composition, we obtain exactly the inverse of this output. So the idea is we are looking at the inverse of some homomorphs coming from moves, and we want to describe them using this extended path homomorphism. And I only put this for the outsplit, but we have other moves, have the shift move, and then the example that I gave about matrices, again, it can be seen as this kind of this decomposition. And when we go further, which is future work, then when we talk about relations, then the idea is that we do not need to decompose, just going to have one relation between the inverse groups, then have just one map. But for now, we need this decomposition unless we have this maximal outsplit. We are looking now at trying to do this at several vertices at the same time. This is just for one vertex, but we could do at several vertices at the same time. But then, and again, for using only extended path homomorphism, we need to take this maximal outsplit at every vertex for the formulas to work. But yeah, for now, for this outsplit at one vertex, we can always decompose in this way. And then that's it.
Muito obrigado. Okay, any questions from the Zoom? Tomek, you are muted.
I'm good.
Okay, you are good. Anybody else? Ali, Adam,
I'm happy, thank you.
Francesco?
No question.
Okay. Jean?
Okay, so that's a chance to say hello to GILLES. Yeah, no, I don't have much to say because I'm not so familiar with graphs. But what's for sure is that inverse semigroups are much more appropriate even to construct the C-star algebra than groupoids for graphs.
Yeah, it's much more direct, yeah.
And also, I should ask Gilles, have you looked at invertible extended graph homomorphism or invertible relation morphisms? Can you characterize when two graphs are isomorphic in that sense?
I don't think we actually studied this because the thing is that we are looking more interested in the sister algebra than the original categories. And of course, if you have the isomorphism in the category, you're going to give an isomorphism between the algebras. But the converse is not really true in general. So you could have the sister algebra being isomorphic by a relation morphism, but the relation morphism itself is not invertible.
Yeah.
So that's why we actually not really looking at this problem.
Yeah.
Okay, thank you.
But I agree with you, Jean. When Gilles was teaching me this inverse semigroup magic, it was really like magic. this is an area of algebra I was completely unaware of, and I was surprised how many non-trivial strong theorems you have with such a limited structure, how general it is. And then as you said it, in the context of graphs, I mean, this inverse semigroup is just extremely natural. Yeah. And then to be able to take care of this first conjugate relation, just by saying, I have a semigroup homomorphism. Again, it looks like magic to me, because remember, when you just try to look at the graph homomorphism that satisfies the first conjugate relation, this is target bijectivity, which is a very non-trivial condition. Okay, and somehow everything is built into this inverse semigroup. So that's very, very much enjoyable. Okay, anybody else who has a question or comment? Please don't be shy. Okay, Tomek, you changed your mind.
Okay, so I would follow the question of Jean. My question is there no purely combinatorial criterion for a sister homomorphism of graph sister algebras given on standard generators by an explicit formula to be induced by an admissible relation or an extended path homomorphism?
Not really.
Yeah, I think only if you have.
Okay, so you start from defining a star homomorphism. Of this should this has to be defined on the classical generators projections and partial isometries by some standard formula. Okay, can we then say when this homomorphism comes from an admissible relation or an extended path homomorphism?
Yeah, I think if you want to look at the admissible relations, you need that the projection associated vertex to be mapped to a sum of projections, and then the elements in the sum are going to be diversity related to the original vertex. And if you want to look at edges, then the edges need to be written as a sum of paths. You cannot use, if you want just relations, you cannot use the stars, just the sum of paths. And also you cannot use other coefficients. Yeah. You need just to be one. So you just really need to be a sum of these paths. So for instance, I think if you look at the gauge action on graph algebras, if you take something which is different from one, then we cannot recover this from the relation of path homomorphism.
Of course.
Yeah.
So the prerequisite for this question is assuming that these relations, this formula on standard generators has only 0 or 1 coefficient.
Yeah, it's sum of paths of. And if you want to use this extended path homomorphism, it's not even a sum. You just need one element. So you need to send a projection to some kind of path alpha star, and you need to send an edge to some kind of path alpha beta star. Ain't no sum over here. And even if you go further, if you go to the group point model, also you do not recover the gauge action, because even the group point model, we are going to send the characteristic function to characteristic function or sum of characteristic function. So again, you can only have a linear combination for all coefficients being 1.
Okay.
So you see, Tomek,
yeah.
when we did relations, then basically what we achieved, that star homomorphism, which is of the form you take your generating projections or partial isometries, and you map them into polynomials. You map them into polynomials again in terms of projections of partial isometries in the other algebra. So this is what we achieved with relations, that we can have polynomials. But as Gilles told you in a very simple example, to write an inverse, you need an adjoint very frequently. Okay, so we decided to do it slowly. Of course, we plan to do it for relations at the end of the day. But to begin with, we just took these path homomorphisms of graphs, And we extended this category so that now in our monomials, it's not only that we have arbitrary positive powers, but we have arbitrary powers period, which means adjoints appear as well. Okay, so I believe that when we combine it with relations, we'll have polynomials, but this will be no longer polynomials just in these generators, but generators and these adjoints. Okay. So this is as far as we should be able to go in our pure combinatorics. But there is no way we can have coefficients in our polynomials different than 0 or 1. Yeah, that's not attainable by combinatorics. There's another actor coming into the game on the stage, coefficients. Yeah.
And that's something that gave us a trouble when we are looking at our relations, because when you have these maps which are just some with coefficient 1 and you compose, then the composition does not really necessary to give you a coefficient 1.
Exactly.
That's one of the examples that we obtain that we have a coefficient 2, and then, okay, this is where we had so much trouble when we are defining this relation morphism before.
Exactly. Yeah.
Okay. Thank you.
And okay, so do you guys have any questions?
If I understood it well, the coverings on the graph inverse group works like the sp2 relation. So,
Yeah.
So is this related to like the Booleanization of the?
Yeah, you have this tight Booleanization. Yeah.
That's what you have to explain to me, this tight thing.
Yeah.
Okay. Yeah. Anybody else? No. Anybody else from the Zoom? So before we thank Gilles again, let me somehow reiterate what else we've got, and he didn't cover. So outspeed fine, we also have multi-outspeed fine, but then there is a very important move called shift. And the shift move is given by a path homomorphism, not by a graph homomorphism. This is a covariant construction, okay? And again, much in the same spirit, we say that absolutely any shift move can be implemented by a path homomorphism. However, to get the inverse, again, we have to have a certain assumption. For instance, we must not allow loops emitted at the regular vertex at which you do a shift. And then if there is no such a loop, then we can write the inverse morphism using some magic with contravariant induction and an extended path homomorphism. Okay. And finally, much like you have outsplits, you also have insplits. So just imagine that now you partition edges that come into a vertex, not that come out of a vertex. Okay. There are different rules of engagement, and most importantly, what happens that if you make an outsplit, your derived new graph generates a Leibniz path algebra or graph sister algebra that is merely Morita equivalent to the initial one, but not isomorphic. However, the point is that if you do two such insplits in two different ways, then these two different ways are isomorphic. Okay, and then just to write down this isomorphism again, we need an extended path homomorphism. So we basically cover these situations, and maybe also it's worth remarking that some people do shifts and some people do unital reduction. So for instance, Soren Eilers and F.N. Ruiz, they do unital reduction. And this is basically the same move, but in the opposite direction, which shows, in my opinion, the usefulness of our functorial approach. Because for us, it's a morphism. A morphism is going into a given direction, okay? So whichever way, because your move is a cooking recipe, okay? And we made these cooking recipes functorial. And now it was for us crystal clear that unital reduction and shifts are mutually inverse moves, at least under some assumptions. And again, much of this will be covered next week by my talk, in your functional analysis seminar. Okay, but for the time being, let us obrigado, Gilles, again.
Thank you.
Let me stop recording.